Remember this stuff? Voltage pushes current round a circuit. I promised you an easy formula linking them. And here it is. Voltage, symbol capital V, equals current, symbol capital I, times resistance, symbol capital R. Voltage push is measured in volts, current is measured in amps, and resistance is measured in ohms, and the shortened way of writing this is the Greek letter O. Don't overthink that. Using an English letter O would look too much like a zero, so we have a wee switch to Greek. No biggie. If V goes up, I goes up. If V goes down, for example, your phone battery being dead, I goes down and eventually stops. If R goes up, for example, rust on battery terminals you've left in a remote a long time, I goes down. If R goes down, for example, you touch an electric fence with water on your hands, I goes up, which is why you get a hell of a worse shock. Worked examples are good for the soul and quite fun too. Have a read of this one and think what you would do next. Come on, do it. Here's the shopping list. Formula. Numbers in. Final answer needs units. 3 ever so slightly harder ones now. You can do this thing though. Bring it. Have a look at this series circuit. Now have a read of what they are asking for. What with the circuit being series, we know that the current will be the same in all parts of the circuit. We can pretty easily find total resistance. We've got circuit voltage. Then we can solve to find current, I. Please note, and this is important, I've not included in this video how you find total resistance in a circuit. There are other, better videos that do this. I have put them in this playlist. You need to go and watch them to find out how you work out the total resistance in a circuit. If the components are in series, like this circuit, then yes, it's kinda simple. But parallel circuits are a whole other game and I don't want you to miss out. That would be emotional. Part B asks us to calculate the voltage push across just the 20 ohm resistor. I will shut up and let you look at what we do. Make sure it makes sense. Question 2 of 3. Have a read. It's not a bad idea with circuit questions to let your eye be drawn to where, or what, you have most information about. And also notice whether the circuit is series or parallel. Here, we have most information about bulb 1, so let's go from there. Look what we do. Circuit questions are a bit like doing Sudokus. You might have the kind of brain that loves them, or the kind of brain that finds them fiddly and frustrating. If that's you, the advice with circuit questions is stay chilled, don't try too hard, and as I've mentioned, let your eye be drawn to where, or what, you know most about, and notice whether the circuit is series or parallel. Gently, gently catchy monkey. And here's how we do part B. Question 3. We are truly stomping to the top with the wind in our teeth. Hang in there. What do you notice about this circuit? If you notice that these are parallel circuits, then jolly good show. As they are parallel circuits, we know therefore that each separate circuit gets full battery voltage. Then we just carry on. The second branch, we do in exactly the same way. These cheeky wee formulas, by the way, are on the formula sheet, but are sort of optional. You can do circuit questions just like we have been doing so far, noticing whether the circuits are series or parallel, then going with V equals IR. These formulas are sort of shortcuts. People who don't really like maths are probably better sticking with what we have been doing. But if these formulas look pretty okay to you, I have put another video in this playlist that will show you what to do. It's good of these other physics teachers to put up their stuff for free, so make use of it. Do you remember the whole V equals I times R thing? What follows is a way of really accurately finding the resistance, R, of a component, using not just a single V and a single I measurement, but a whole bunch of them. The following is how we do it when we want a really super-duper accurate resistance measurement of something. Dodgy Bob won't do this if he just wants to shove the correct light bulb in a mains circuit. Set up a really simple series circuit as shown, with the component to be tested in series with an ammeter and variable voltage supply. You can set the variable voltage supply at a whole range of different voltages, and for each voltage, write down what the current is. Then, plot these V and I values on a graph. Put a line of best fit through your points. Please note, points should be plotted as neat little crosses, not ugly great blobs. Axes should be labeled, and this includes units. And a line of best fit should have pretty much the same number of points above and below it. A line of best fit is not, and is never, a dot-to-dot affair. That is a nasty biology thing. Of course, they prefer bar charts anyway, because they can then color them in. Stay within the bars to get that top grade. Anyway, if your current voltage graph is a straight line, then firstly we can say that the component follows Ohm's law. Then secondly, we can read an I value and a V value from the line of best fit, from which we can calculate a really accurate value of resistance, because we have used that line of best fit, using V equals I times R. Finally, for this video, the voltage from a battery pushes in one direction constantly until the battery runs down. So the electrical current is pushed round constantly, in one direction, as well. Did you know, the electricity topic was where the band got their name from? You see, young physicists get everywhere. A graph of current flow looks like this, and the current is described as being direct. The voltage push from a AA battery is 1.5 volts. The voltage from the mains, in other words from a power station, pushes forwards, and then it pushes backwards. One forwards push and then one backwards push happens 50 times a second. And the push forwards and push backwards are pretty strong, 230 volts each way. So the current is pushed forward, and then backwards, constantly, when a circuit is connected to the mains. In a sense, the electrical current doesn't go anywhere. A graph of voltage push is like this, and the current is described as being alternating. The reason mains voltage push goes forwards and backwards and forwards and backwards and forwards and backwards is that it comes from huge spinning magnets that spin towards and then away from any particular point in that circle. No need to know that, but that's the reason why.